implies conditional convergence, but not the other way around. So let me say it in words. So let me recall. So you start with an, okay, so 1 to infinity. Absolute convergence means the related absolute value series converges. Okay, so if this one is absolute convergent, absolutely convergent, or convergent absolutely, which means this situation, then the original series itself is convergent. So in other words, i.e., absolute convergence implies convergence. But convergence, if you just say convergence, convergence doesn't imply absolute convergence. That's what we learned last time. Okay? So here is the example. Here is the example. Let's say if I say 1 over n, that's what? Divergent or convergent? Divergent. Right? That's called harmonic series. That's P series with P equal to 1. That's divergent. But if I make it alternating, then this one becomes what? Convergent. This one convergent, but not what? Absolutely convergent. That is to say that if I wipe out the sign, just look at the absolute value sequence, and then their sum, is divergent. So, and this one itself is convergent simply because you somehow have this cancel away, right? So that kind of situation brings us to, I first have this issues of absolute convergence, the concept of absolute convergence. So absolute convergence means if you wipe out the sign, you have this absolute value terms. Then if the sum of them converges, that's called, then we say that the original series absolutely convergent, or convergent absolutely. And that's a very strong condition, all right? And therefore, if you only have a situation in which the series that you begin with is convergent, like that one is, yeah, granted it's convergent, but that doesn't mean that it's absolutely convergent. Okay? So absolutely convergent is a stronger condition. And if you see that it's absolutely convergent, of course it's convergent. Otherwise this phrase absolutely convergent is kind of weird. So if you say absolutely convergent, of course it's convergent. But convergent is not absolutely. Okay, then that brought us to this concept of conditional convergence. So conditional convergence means what? Means okay, it's convergent, just like that one, that's convergent, but what? Not absolutely convergent. That's what, you have a little bit of reservation. That's called absolutely, that's called conditional convergence. So it converges conditionally. And that still converges. That still converges, granted. But unfortunately, it doesn't satisfy that stronger condition, which is absolutely convergence. And therefore, we point to this one, you say that, well, it's convergent, but its absolute value version doesn't converge. And therefore, it's not, therefore, this original series is convergent, but not absolutely convergent. And that's exactly what conditional convergence means. So this one converges conditionally. And weird things happen when a series is conditionally convergent. That's weird going to learn about very soon. But that's not our main concern. So I don't want to talk about that until I finish the two tests. One of which we finished last time. So let me just recall. Racial tests. Racial tests. And I want to rephrase it. Because last time, I remember the first time I wrote it, I actually missed one word, and then I later on asked you to add it that way. So let me do it again, just for completeness. So we are concerned about this theory. Okay? And so suppose you look at the ratio from one term to the next. Right? And this ratio, you see if there's a limit. Suppose this limit is L. It actually converges to something. I call that L. And actually, I'm going to write it this way. This is a series. Is that right? So I'm going to say I write absolute value. Forget about a sign of terms. I look at absolute values. And then the absolute value series, I investigate the neighboring term ratio. Right? Ratio of this term to the previous term. So make term over this term. And then there are three possible scenarios. The convergence L has to be positive because everything is positive here. Imposing the absolute value. Right? This may not be positive, but I'm imposing the absolute value. So here everything is positive. So this, if it converges, which it does, according to this assumption, right? Then this one has to be positive number at worst 0. It cannot be negative, right? Okay. So there are three scenarios. If L is less than 1, right? Then the original series, which may not be positive series with positive term, could have negative terms, alternating term, or any kind of pattern. Then this one is convergent. What? Absolutely. Absolutely. Whereas if L is greater than 1, then, sorry, the original series must be what? Divergent. And there's a boundary case, which is L equal to 1. Then this test is inconclusive, which means I cannot, it could be convergent, it could be divergent, I just don't know. Yeah.
I have questions.
Sure.
Like, when before I tried to apply this rational test on one of the quiz. I mean, I tried to apply the rational test on one of the quiz.
Did it work?
It's like it's coming up with it 1 on the solutions.
Yeah. So if it is 1, then that means it doesn't help.
Yeah.
Right. So that means that this is not a test that can, a lot of problems are like this. Because as a matter of fact, so let me make a remark since you bring it up. That's something that I will talk about later. But since you brought it up, I'm going to just make a comment here. So here's the important observation.
Sorry, Mr. Chen, is that inconclusive?
Right. Inconclusive. That's right. Inconclusive. Thank you.
So in the case of one,
that means that case of one, if it limit of an plus 1 of an happens to be 1,
you have the same.
then I have nothing to offer.
Yeah. So apply another test perhaps.
Yeah, you have to use some other means. We don't talk about